Okay.
Hello, this is the STEM intro session. The presentation was made by me and other CAIVO executives. Here's the icebreaker. We basically have you basically see the examples of certain texts or pieces of codes, and you need to decide which one of them were made by AI and which one of them were made by humans. The first round, we have 2 poems. Poem A and poem B. I'll give you, let's say, 1 minute to decide which one was made by AI. Okay, some of you said that poem A was made by AI and poem B was made by a human. Yeah, so B was made by a human, you think? Let's see what is the actual answer. You were right, poem B was made by a human. It was specifically made by an author called Langston Hughes, and yeah, he was the source of the poem B. While poem A, it was made by AI, it followed a perfect rhyme scheme. Let's look at it. I heard the dream whisper soft and low, telling me where I ought to go. So it rhymes. It's pleasant to read. It lacks the abstract imagery of blue cloud cloth and the emotional nuance of the human experience. So I heard the dream whisper soft and low, telling me where I ought to go, climb the mountain, touch the sky, dream fate when shadows are near. I mean, yeah, that's not really complex or deeply emotional. It is purely technological, something that an algorithm or a function would write instead of a human brain. Um, the next round could be more complex since it is code and it is bound to computer rules. So I also give you 1 minute to decide which one of these pieces of codes was written by AI and which one of them was written by a human. Okay, so we think that option A was written by a human and option B was written by AI. Um, I mean, yeah, you have reasons to suspect both of the things since option. Oh, you have different opinions. Some of you say that option A was a human, and some of you say that option A was written by AI. Let's see the actual answer. Code A was written by a human. While option B is perfect and PAP8 compilant and generic, it is exactly what Copilot or ChatGPT would generate for create a user for a database prompt. So you see, it defines create a user function in Python, which then inserts a user record into the database and returns a result, returns a Boolean result. It also has some specific comments and it generally lacks human imperfection in it. That's why it is AI. And option A includes legacy sync context. Yeah, we have legacy sync, the V2 that the database requires. It has good general explanations of why it does certain things, while AI just states that it does something. And round 3. These are pictures of arrows. You need to tell me which one was generated by AI. Again, I'll give you 1 minute to decide. Okay, I see responses that rows B was made by AI, and honestly, I think I know why, because this kind of looks unrealistic, and let's see what is the actual answer. Um, Art A was made by human, therefore B was made using AI, and this is the author of picture A, or art A. Throughout the whole STEM course, we'll have several topics, such as AI in space, AI in cybersecurity, in military, in robotics, etc. So we're gonna tackle all of them and see how our lessons, our fundamentals of neural networks can be applied in these topics. Do you want to add anything, Evan or Prateep?
Oh no, this is just like our STEM topics we plan to cover within like the next month or years. So yeah.
Yeah, we're not gonna see all of them, but you definitely will see a vast majority of them, and it's gonna be interesting. Here's our rough schedule of how the topics will be tackled. So we'll have 2 weeks of input sessions in which we, officers, will present some professional lectures, teachings, and general stuff you need to remember. And then week 3 will be focused on pure output. What it means that you will be making research papers, presentations, or, or posters, sorry, or maybe create applications on a given topic. And now let's start the actual learning of this STEM intro session. So today I'm going to talk about activation functions. Um, I talked about them briefly on the intro session for the whole CAIVO organization, but briefly activation functions, they determine whether a neuron should fire or stay dormant. Or in other words, whether it should activate the input, like multiply it by certain values and add something to it, or it should just sleep and do not change the input. Activation functions serve as gatekeepers, mapping some input values to specific output ranges. What that means, it basically normalizes the outputs of the neurons. If you go into calculus and maybe computer science, you have a normalization topic in vectors. So some of you probably know this already. Yeah, here is the reason why do we need activation functions. As you can remember, a neuron is typically a linear function. So y equals mx plus b, in which m is weight and b is bias. And linear functions, they are good for binary patterns where we have two groups with a clear distinction of them. But in such examples as with this graph, where we need to make a neural network that categorizes 2 points into two separate groups, as we can see, a linear model cannot fully do this. To correctly address this issue, we need a nonlinear model, as you can see here. So it goes like this. and it is more accurate than the first one. Um, so without nonlinearity, a neural network is just a linear regression, which is limited to simple straight line patterns, as I said before. And the activation functions allow the neural network, to learn curved decision boundaries and complex real-world relationships, because nothing in real world is binary. And it works even more perfectly on multidimensional graphs. I cannot really show them right now because, I mean, it's kind of hard to show a 3D graph, not talking about 4D graph. So I'm sticking to 2D graphs here. Um, so here's how activation functions relate to neural networks. Here we have a simple neural network, a simple neural layer, which consists of summation of all weights times all inputs, and then plus bias of this layer. This is the content of previous lesson, by the way, just the brief of it. And then activation function simply takes this value as an input to it and applies a certain function to it to kind of change it and clump between two values. Okay, next slide. Some of the examples of the activation functions are sigmoid, or they're also called logistic functions in biology. They map inputs from 0 to 1. They are ideal for probabilities in binary classification, because probability can either be can be mapped only from 0 to 100% or from 0 to 1. Then we have hyperbolic tangent. It maps from -1 to 1. And it is zero-centered, which means that it is centered around 0. So it can go it can go like this, while normal sigmoid can only go like this. That's a rough presentation. On the next slides, you're going to see actual visualizations of it. So yeah, hyperbolic tangent is also useful for model convergence. And here how it looks like. In neural networks, we are also using derivatives, which are used for backpropagation, which is the topic of the next lesson, by the way. So which is why I included derivatives of these functions here. So here we have hyperbolic tangent activation function and then sigmoid activation function. And you probably can already see the problems with it. You see right here in this area, the outputs of the neurons or outputs of activation functions, they become really close to 0, which can be a problem with certain weights and biases, because computers, they don't really like very small values or very large values. So at very small values, they don't really behave correctly. There could be some bugs in multiplication, which can very damage the process of learning. Same goes with derivatives. The closer derivative is to 0, the harder it is for a computer to see the difference between two different derivatives. So, for example, this point is almost identical to this point for a computer, which is a problem while training, of course. Then computer scientists made a very, very good solution for it. It's called the ReLU, which is a rectified linear unit. This is by far the most popular hidden layer activation function. It is very simple computationally. It is very efficient. Like, in my opinion, it is the most brilliant solution they ever made for neural networks. It looks like this. It kind of shoots two problems at one time, because it is very computationally efficient, because it is simply a max function between 0 and the output of a neural network. And computers love these simple functions because they're very easy to perform on an assembly level. Because hyperbolic tangent and sigmoid function, they depend on e to the power of x function or the exponential function, which is very computationally inefficient. and it can reduce in mm, it can be inaccurate for computers since E is an irrational number. But a single value isn't enough for computers, for neural networks, because I mean, it's a simple function, and for example, for very big inputs, it can damage the processors because they don't like big numbers. That's why we have certain variations of ReLU, one of which is leaky ReLU. It is called leaky because it leaks certain values that are close to zero. For right here, as you can see, instead of mapping from 0 to x, instead of maxing from 0 to x, it maxes from 0.01x to x, which means that it allows for a very small gradients for negative inputs, which can avoid dead nodes of neural networks. And then we have exponential ReLU. It combines the beauty of sigmoid function, uh, which is including e to the power of x, with the beauty of normal ReLU. It smoothes out the negative regions and pushes the mean activation towards zero. Let me clear the annotations. So here, how it all looks like. We have normal ReLU, which is the blue line. It's kind of hard to see here because of the other functions. You see how it looks like. But then we have slicky ReLU, which is right here. It kind of looks like normal ReLU, but on very big inputs, it smoothes out. Then we have GELU, which goes like this. And it has certain use cases in certain neural networks. And for other functions are swish, sigmoid, swish and sigmoid. Sigmoid, we already talked about it. It's just a normal clumping between 0 and 1. It's smooth clumping. Yeah. And GELU, Gaussian error GELU, is actually very common in GPT models and BERT models because it weights inputs by their probability in normal distribution, as we can see here. It is like normal GELU, but with certain advancements, and it depends on the implementation. So I didn't find a formula to include here. And swish is called a self-gated function, which is basically x times sigmoid of x. It combines normal output of neurons with a sigmoid function. It is used in neural network called efficient net, and it is known for being smooth and non-monotonic. Oh, and to sum everything up, we can see that sigmoid is gradient flow. You see how it smoothes. It basically is saturated. And the ideal use case for sigmoid activation function is for binary classification. For example, classification between a dog and a cat, or maybe a car and a fire hydrant. So it is used in those kinds of neural networks. It clamps values between 0 and 1, as we can see. Then we have ReLU. In this case, it's really leaky ReLU and normal ReLU, which are excellent for excess more than 0. Because you can see if they're less than 0, they just clamp to 0, which is non-ideal for certain networks. They are basically a standard for hidden layers of neural networks. GELU is the next one. It approximately goes from negative 0.17 to infinity. It is range. It is very smooth, as you can see here. It is used for transformers, which are a whole certain topic I will probably teach on the next weeks. It is Jello is the standard for neural language processing, by the way. Even like Gemini and Grok uses it. Yeah. Um, Thank you for your attention. Thank you for your attention. Do you have any questions?
It's your time to ask questions now. If you guys have any questions? Uh, Anyone have any questions about this?
I mean, you could have questions for the use case and for the implementation of activation functions in neural networks. But since we only know the concept of neurons and activation functions themselves, it's kind of hard to tell how to implement it. I will probably tackle this topic on the next lesson with backpropagation, because this is when activation functions really thrive. This is when you can see why do we even need them in the first place. And the activation functions are mostly used for the learning purpose, since real neurons do not have activation functions.
There's a question in the chat.
Oh yeah, I forgot about chat. I'm still confused about this in general. Can you explain the different activation functions more? I mean, it is
Like essentially, it's like
indeed,
a math. It's like it's like a mathematical equation, right? And you
mhm.
like basically apply it to like a neuron's output in a neural network.
Yes, you are right. But so Sia, she probably asked about why do we need them, maybe the use cases of it. And the thing is, it is not very known why do we need them. It's just one of the black box problems in neuroscience, in computer neuroscience, since we have like things like backpropagation and activation functions, and we don't really know why we need them. It just works. Basically, just clamp outputs of neurons. What exactly do you mean by the output of a neural network? I mean the output of neurons, since neurons are separate mathematical functions, as we can see on this slide. And here, neurons and neuron layers are just individual functions which with inputs and outputs, and by output I mean the output of these functions. Did I answer your question? Yeah, it just comes with experience with neural networks. I mean the understanding of it, and you can basically think about activation functions for now as clumping of the outputs of the neurons, because in real neurons they have like activation potential, I think, and it is used by brain to it is an evolutionary concept made by brain to um, improve learning, I think. Am I right, Evan? Because you know more about biology than I
Yeah,
do.
yeah.
Articles and resources you can use to learn more about this. Yes, there is a YouTube channel. I forgot what its name, but there's a guy who is a neuroscientist, and he explained this on real examples. Not Yes, you can use 3Blue1Brown. There are certain videos from 3Blue1Brown, but he tackles general transformers, and he assumes that you already know this stuff already. You could also you could also read real research articles by Google. I can send it in the band, like top 5 research articles you should read before learning about neural networks. It's going to be hard, but you will have a great understanding of it. You're welcome. Yeah, do you have any additional questions?
Thank you guys for attending this meeting. If you were here for that, it very much helps. Next week, the STEM will start their first topic, which I think is AI in space, because like that those slides are already made from last time. Um, So yeah.
And the next learning objective will be backpropagation, which is the training of neural networks itself. It's going to be even more interesting. Yeah, bye everyone.
All right. Bye.